Okay, in the beginning of the year, we talked all about how there are physical reactions and there are chemical reactions. And most of the stuff that we've been dealing with is a chemical reaction. Something is going to be irreversible. So today we're going to talk about what influences our reaction rates. Okay, what makes milk go bad and food spoil faster than others? What happens if you accidentally add a drop of bleach to your dark wash versus if you add a cup? And what dissolves faster, granulated sugar or a sugar cube if you were to put it into some hot tea? Or what if you put it into cold tea? So there are some major factors that are going to influence our reaction rate. Now, rate is something that you'll talk a lot about in physics, and rate is a measurement of the frequency of a successful reaction over time. So we're mainly going to use molarity per time. So molarity per second or something like that. And kind of looks like meters per second. And there are four major factors that influence the reaction rates. The reaction concentration, so how strong the molarity is, the surface area, how spread apart they are or how close they are together, the temperature, and the presence of a catalyst, which I'm sure you talked a little bit about in biology class. But what we're going to do is we are going to look at these in terms of the collision theory. So how will these four things affect the activation energy, that energy you need in order to have a successful reaction, and the positioning or the proper orientation so that you do have a successful collision? So let's take a deeper look. First, let's concentrate. Whoa, All right, so concentration is going to be how many moles of our substance we have in a liter of solution. Okay, we know all about our molarity. Okay, reactions will go faster when you increase the rate of when you increase the concentration. Okay, so if you have a greater molarity, then you will see that the rate is going to increase also. Now, this is going to happen because you are going to increase the number of reactants in your volume, and you are going to, in essence, increase the number of successful collisions. If there's more stuff in there, more of them will have a chance to have the right energy and to have the right orientation. Okay, dilute solutions that don't really have much won't have a lot of solute in them, whereas your concentrated solutions will. So you'll see that you will have more reactions successful over here, and you will have less reactions successful here. Okay, so that's pretty much a no-brainer. The more stuff there is, the more it's going to occur. Okay, surface area. Surface area is how spread out things are. More surface area means there are more molecules and more atoms that will expose to the reaction collisions. Okay, you have granulated sugar, you have sugar cubes, you have confectioner's sugars, which is called 10x, which is the same thing as this sugar. It is just 10 times smaller. Okay, so it is going to have more chances to have a successful collision. Okay, I always say, what can you feed more birds with in a shorter amount of time? A loaf of bread, okay, kind of looks like a mushroom, but that's my loaf of bread, okay, or breadcrumbs. Well, duh, I can feed more bread if I have breadcrumbs, or more birds if I have breadcrumbs, because it's going to be spread out. And this is why medicines say do not chew or crush, swallow whole, because you don't want all of your medicine that is usually formulated in a time release capsule to be released all at the same time so that you get the right amount of medicine over the right amount of time so that you don't accidentally, poison yourself in some way or get relief instantaneously, but then not again for the next 4 to 6 hours. Temperature. Okay, what happens when we have our temperature? Well, the average kinetic energy of a substance is going to increase with the temperature. So we know kinetic energy, for all intents and purposes, is the same as our temperature. So if we increase the temperature, we're going to increase the number of particles that are going to have the correct minimal amount of EA. So that means the molecules will move faster and at higher temperatures, so they will collide more frequently, and if they collide more frequently, the more success. So temperature is usually a big one. What will spoil faster? Milk that's in the refrigerator or milk left out in the sun? Obviously, the milk left out in the sun because those particles are going to be moving faster. Temperature has such a significant effect on reaction rates that typically the rate approximately doubles for every 10 degrees. So that's going to go up exponentially. All right, so you're going to see that the relative rate of the reaction and with however many molar per seconds we end up seeing is going to almost double for every 10 degrees that we end up going. So we can see that things are definitely going to speed up the warmer it is. Okay, and likely you'll see, conversely, that the colder it is, you are going to see the same amount decrease. All right, this is a very successful diagram that shows you the minimum amount of energy that is needed for a successful collision in hot and cold systems. All right, so these two graphs here, these two lines have the exact same amount of particles in them. But this one occurs at a lower temperature and this one occurs at a higher temperature. Okay, so this is the fraction of collisions. And this right here is the collision energy. This is the magical barrier, that minimum amount of energy needed for a successful reaction. At lower temperatures, you're going to see most of them here at this peak where you end up having these collisions occur, but they're not going to be very successful. That's going to be like when you bump elbows with somebody in the hallway and it doesn't really do anything. All right, and you have this tiny little area right here that are going to allow for them to be successful. Whereas if you heat this up, this curve here, okay, pushes down here, but this curve here expands this way. And when that happens, now you are going to see that this amount of particles is going to be successful. That would be like if you ran through the hallway and you were bumping elbows, and instead of just bumping somebody, you're actually knocking the books out of their hands. All right, so you're going to see there's going to be more successful um, collisions and reactions at higher temperatures. All right. And then lastly, we have our catalysts. We know that catalysts are going to help a reaction by altering the pathway in which they take in order to make your reaction. They are not consumed, so they're not a reactant, they're not a product. So if we talk about our hydrogen peroxide breaking up into water and oxygen gas, if you add some sort of iodine complex, okay, like Ki, you're basically just adding um, in your iodide molecules, okay, it is going to allow for this stuff to occur and change much faster than if it were to just happen on its own. Okay, so it increases the rate of the reaction. And the way that it does that is that it makes a new lower EA. And we'll talk about this later on in the other videos as well. Okay, I couldn't find one where the uncatalyzed came first, so we'll go over this one first anyway, and then we'll do the one on the left. So in an uncatalyzed pathway, you see your reactants are here and your products are here, potential energy and the reaction progress, the reaction coordinate, time, whatever you want to call it. There's many different ways to label the same thing. Okay, you see that this is your EA, the difference between your um, activated complex up here at the top and your reactants. What a catalyzed pathway does is that it is going to drop. Okay, it's going to drop the original EA, and this is going to be your EA catalyzed one. And it usually breaks it up into a different reaction mechanism where you have like two steps to do. So this would be EA catalyzed, this would be the elementary step one, and this would be your EA catalyzed elementary step two. But these guys are going to be far less than your EA original. All right, so that's what it does. It drops the pathway down. It would be like putting a ladder or a bench right in front of a fence and you had to hop the fence. Okay, it's going to take far less energy than it is if you don't. Okay, if you have that series of steps that are going to be in front of it. All right, so that is our factors that influence our reaction rates.